Oh no, it's time to cause trouble once again with folks who don't understand what hardware RAID is and how it continues to actually be dead.
お前はもう死んでいる。何?
Hardware RAID is dead. We don't send drives through physical controllers anymore. That's not a thing. This time, featuring SupremeRAID. They bill themselves as the best solution for NVMe RAID, and I have put it to the test. And I put it to the test against Linux MD multi-disk. The goal of their product is to go fast. And go fast it does. They've come a long way, and they've added a lot of features over the last couple of years. I set a number of traps for them. How do they do as we stumble through the traps? There are a lot of people out there that are looking for hardware RAID controller in their modern server with 128 cores and beyond, and they stumble into this without really understanding what this does. This doesn't resemble the hardware RAID controllers of yesteryear, and I really want to get that across and help you understand how this works under the hood because it's really neat. Nevertheless, it does use hardware to accelerate beyond what you could do with a 100% CPU-based solution alone. But it's still a bit of a stretch. Grade's SupremeRAID is a CPU-accelerated software RAID, effectively. To the tune of about just 180 gigabytes per second from 16 CM7 Kioxia storage devices, nearly 20 million IOPS. But what's the catch? We're going to talk about everything, not just, also the fun stuff. If you've been following this channel for a long time, you know that we've gotten into a lot of AI stuff. It's actually really exciting. Folks in the level 1 community, and I've been along for the learning journey, have done some really amazing things with quantizing models and getting things to run, and it's chewed up a lot of space. Kioxia sent us a lot of storage, and I've been experimenting with, redundancy in these large storage volumes and things that we're working on for AI. Grade offered to sponsor some content. They're like, we think that you'll like how much engineering we've done over the last couple of years. Sponsor a project or sponsor a review or whatever. I turned them down. Because I knew what I was getting into. Or at least I thought I knew what I was getting into to take a look at it and see what's up and kick the tires. The other thing is that since I've been doing the Hardware RAID is Dead series, there are a lot of militant folks out there, some of which misunderstand things, and some of them say is like, yes, look, the level of data integrity that ZFS provides is amazing, but there are kind of a lot of downsides in terms of performance, and we really need things to go fast. And I've become personally acquainted with that in the AI context. So let's do a deep dive and take a closer look at G-RAID on our blisteringly fast Kioxia CM7 drives that Kioxia has let me borrow for a while to be able to do that. 15 gigabytes per second per drive, 16 drives in a chassis. Let's get to it. Understand that also today's video focuses on locally attached NVMe, meaning it's plugged into your server. But this solution can also be used with NVMe over Fabric, or even SAS or SATA mechanical hard disks, or other kinds of disks, or SSDs. But it works best with locally attached NVMe and up to 32 physical devices. It supports RAID 0, RAID 1, RAID 5, RAID 6, and RAID 10, and it supports configurable data stripe sizes from 4 to 128 kilobytes. So, what's the architecture look like? It's NVMe drives plugged directly into your CPU's PCIe lanes. Yep, that's right. The NVMe is still attached directly. The software does a lot of clever things, and RAID parity calculations happen on this PCIe add-in card here, which is actually an NVIDIA GPU. The magic of GPU Direct here, as well as direct access for the NVMe queue from user space, because they've incorporated SPDK, which is a lot of fun, and you should look into and fun stuff. And of course, because you've got direct access to the devices, you can do smart diagnostics and monitoring and that sort of stuff is still possible, although their driver does some fun things to hide that, but it's still accessible if you know what you're doing. Our test system, it's a dual Intel 6980p system, and it is the absolute top of the stack speed demon, 128 cores from Intel, and that's in our Gigabyte R283 chassis. We've got a lot of videos about that chassis, you should check it out, it's a lot of fun. We've covered this system in a bunch of other videos and a bunch of other different configurations, but suffice it to say, this is a monster workhorse system for us. One of our disk test configurations is around 16 of these CM7 SSDs from Kioxia in that chassis. In a block diagram of our system, though, you should understand that 8 are attached to PCIe lanes serviced by the first processor, and the other 8 CM7s are attached to PCIe lanes that are serviced by the second processor. So we have 2 groups of 8 disks, effectively. These drives are fast. Individually, they're up to 15 gigabytes per second read and write. That's Gen 5 storage at full saturation. And our chassis is designed for more modern E3 SSDs. So this is maybe a little different than what you're used to seeing in U.2. We also have our grade card. This is essentially an NVIDIA GPU. The entry level is interesting. It's a T1000 GPU, but I think if I were doing this in production, I would start with the A2000, which is a PCIe Gen 4 X16 card that also supports ECC mode with its VRAM, which is kind of important to me. And the other question top of my mind is, what does this get you over a full software solution like Linux MD? Isn't Linux MD just coming relentlessly with all the AVX 512 and speed optimizations? Isn't this a lot like a software solution? I mean, you aren't expecting anyone to build a RAID controller where the drives attached to the controller, right? Like it would have to go through PCIe. I mean, think about it. If your NVMe passed through a PCIe controller, 4 of these would saturate 16 lanes of the controller. And the controller doesn't do anything for you except add overhead and latency. Are you going to have 4 controllers that have to work together in concert somehow over the PCIe bus? Well, that sounds like what we're already doing with the direct NVMe, just with more steps. Oh, and if you want to run 2 controllers, like 2 of these attached to each CPU socket, each NUMA node, so that it's more local to the drives, you can do that. I didn't test that, but in redundancy mode, I was pleased to see that the use case for that is covered in the documentation. So it's like, oh, the GPU died. Oh, okay, there's another GPU that can pick up and go. That is nice to see that level of failover, and it's nice to see that tested. So let's take a closer look at the benchmarks. All right, so the first thing to understand with the benchmarks is that the grade solution now actually does what it promises, at least as reasonably as I think it can, in terms of a RAID solution, redundancy, and performance, and it's well put together. It's well put together in 2025. So, top line number, best performance that you can expect, 175 to 180 gigabytes per second from 16 drives, with a write speed on the order of like 80, 85 gigabytes per second. This is really interesting though, because with 16 drives and the physical configuration on a gigabyte chassis, there's 8 drives per NUMA node. And that also had more of an impact than I expected on our overall benchmarks. And so, I think that if I were running this server in a real-world configuration, I think it would actually have 2 volumes of 8 drives instead of 1 volume of 16 drives. Try to pin my I/O so that it runs on a single node. I think that I would rather, if I'm interested in the top-line performance number, I'm going to get better performance out of the 2 volumes, and maybe I could just, like JBOD the disks together. It's like, okay, when this one fills up, do the other one, or create an LVM volume of the 2 of them. That has better overall performance, and that may be something we could discuss in another video, especially for like the AI use case. Real world performance here though is very good. Our real world performance, 964 microseconds, is very, very good for a solution like this. Notice that, in a couple of scenarios, it's like, oh, it looks like it's 269 microseconds when we're dealing with a 16K block size and a thread size of 1. This is a little misleading because of the tools that I have to do this kind of benchmark, but it's on the order of like 100, 200, 300 microseconds, give or take. And look, the overall performance is pretty low at 145 microseconds, or low is a good thing, between 64K block size and 32 threads. So this is very, very good performance. I mean, 964 microseconds in a worst case scenario in a kind of an overloaded situation is very good. And the performance in a real world scenario with, 64 threads in a 1 meg size at 62.9 gigabytes per second is quite good. I'm very satisfied with that on an 8 drive configuration. Understand also that this is RAID 0. Our GPU, our T1000, really isn't doing very much here. This is just, if any drive dies, I'm going to lose the complete volume. And that is not normally something that I would recommend that you run, but I ran a RAID 0 configuration so that I can have a cleaner comparison to Linux MD and some stuff that we're going to talk about in a second. Now for RAID 5, with 8 drives on a single NUMA node, again, extremely, extremely good. Our latency only goes up to 1100 give or take, microseconds for latency in a worst case scenario, and overall our heat map here for latency is very, very good. Now, a lot of you may not realize how much overhead and insanity the file system can add, and that there are knobs and tunables for tuning the file system. So if you just mkfs.btrfs a volume like this, you are leaving an incredible amount of performance on the table. The write performance here really is not fantastic. Like, what is the bottleneck here? It's like, well, BTRFS is writing extra information elsewhere, and overall the performance really is not fabulous when we're dealing with the file system. What about XFS? XFS has journaled metadata. It's not as resilient as BTRFS, but it was originally designed for larger-ish volumes. Larger is not as large as it used to be, but with that kind of a file system, it's doing a little better. Now, XFS also has a lot of knobs and tunables that you really need to step into, but this is the only file system that out of the box I was able to achieve over 100 gigabytes per second read in at least some scenarios. And our write performance here is near our theoretical of 80 gigabytes per second. Now, what about LinuxMD? It's like you step into LinuxMD. Okay, so with LinuxMD and a RAID 0, really, it's not a lot different. So that is still useful. It is still helping with that. I can still manage that. And because of that, you will see improvements in latency more than throughput, and that's you sort of see in the graph here. But LinuxMD, if you're going to run RAID 0, if you're going to play it that fast and loose with your data, then you could use LinuxMD, and it's not a dramatically different experience. You do have higher CPU utilization, interestingly, probably owing to the peer-to-peer configuration. But check out the sequential average read latency if we switch to a RAID 5 situation. The sequential average latency is a fair bit worse in our 1 meg 64 thread configuration. Now, there's also something that's misleading here on the sequential read latency. It's like, oh, you get 9 microseconds with 1 thread and 16K. This is a caching thing, a file system thing. This is a recent change in the Linux kernel. I was having trouble flushing the RAM cache, and so things ended up being cached in RAM, even though I've got 512 gigabytes of memory, even though I'm working with a 4 terabyte data set. It's like, oh yeah, that was cached. So you run it, you rerun it, and some of the blocks here have absurdly low latencies. This only happens with LinuxMD though, because LinuxMD and the way that it interacts with the kernel is a little different. Real world, we're talking 150, 200 microseconds of latency. It's not significantly worse, but it's also not significantly better. LinuxMD also does a weird thing. It's like it should be able to achieve like 50 gigabytes per second read, but at the 1 meg block size, even using a 1 meg stripe size on LinuxMD, 18 gigabytes per second, the performance was really not super consistent, even with the higher CPU utilization. Now, even though our RAID 5 configuration on LinuxMD, finished its resync, the write speed was also absurdly slow. And this is, again, just an out-of-the-box LinuxMD creation with no optimization. If you follow the Level 1 Text forums, this is a thing that people trip over all the time. They create a new LinuxMD array, and the write performance is really terrible. We can get the LinuxMD write performance up to be better, but because of the double journal entry thing, and some stuff that LinuxMD doesn't do well out of the box, our real world write performance is more like on the order of 45-50 gigabytes per second, with our theoretical maximum, our best case scenario here being more like 65 gigabytes per second. So, I mean, real world, I would probably say is on the order of like 35-40. Peak performance is like maybe a little over 40, but LinuxMD really leaves a lot to be desired here with regard to that. Oh, and RAID 6, it's still the case that LinuxMD doesn't trust the metadata if there's an inconsistency. I think LinuxMD should offer more tools to do that. I also, when I was working in the bowels of ZFS and encountering inconsistencies, it was useful to dump a tool or create a tool that would dump all the blocks, and then I could do microsurgery on an individual block and be like, okay, the first half of this block plus the last half of that block, maybe we'll make a consistent block in order that, the ZFS will be happy. You could do the same kind of thing with RAID 5. It's like when you encounter an inconsistency, you can dump each RAID 5 stripe and try to replace each one in turn to try to find which one is corrupted, because you don't know. This is a manual microsurgery type operation. As far as I know, tools to actually do those things in either scenario haven't been developed. That would be a fun thing to do. But in digging into, okay, what sorts of data inconsistency and like scrub type situations can I create to try to test to see how well it recovers, it's doing far better than I expected in 2025. They have made tremendous improvements to the platform and overall data integrity stuff to better align with what's there in hardware while still giving you top shelf performance. So that's nice to see. Now, what about data integrity? It's a little bit the elephant in the room. This is something I've always harped on in the context of, or in all the content that I've done, you know, on RAID and how hardware RAID has evolved in the modern era, and even how I think some aspects of RAID requiring workloads are going to cause a return to the way that RAID was done in the before times. I don't want to rehash all of that in this video. You can check out my past videos that are linked in the description. You know, this one, maybe that one, maybe another one, if you want to check that out. Suffice it to say that one of the most militant recurring misunderstandings that I see is what is responsible for the data integrity. One of the things that I like to do is inject a data inconsistency in one drive in a RAID volume, and then see how that's dealt with by the controller or the software or whatever. Ignore for a second about how the inconsistency came about, because some people seem to get hung up on that. And let's look at the universe of possible options for dealing with that situation, or how that situation can come to be. Suppose we have 8 drives in RAID 5. The data that we have is striped across 7 drives, and the 8th drive contains parity that is calculated from the contents of the 7 drives that contain data. Oh, and understand that which drive the parity is on is rotated with each block of data. It's not like you have a parity drive, it's just on a chunk basis. Suppose no drive is reporting an error in retrieving the 7 data blocks, but something happens and disk 7 does not return the data that had originally been written to it. In most situations, the data is assembled from the 7 data blocks and returned uncorrected. Not only that, but the data corruption remains undetected until the scrubbing process or some other asynchronous process happens where the parity is actually checked at read time. Now, strictly speaking, from just this data, because no drive is telling us there's an error, there's not enough data to know where the corruption lies, at least with RAID 5. When the RAID scrub comes along, and sometimes it's called a patrol read, it'll assume that the parity is incorrect in a lot of implementations, including Linux MD. I mean, the data is scanned along with the parity, and it's like, oh, there's an inconsistency there. Sometimes that gets flagged and logged, but a lot of the time the parity, like I say, is recalculated and the incorrect data is used on disk 7. The data itself is not actually corrected. And this is how SupremeRAID works. And this is how Linux's software RAID works with Linux MD. And for example, you don't necessarily have to have it corrected. It can just flag it and say, hey, this is a situation you want to deal with. And that's that it has that feature has pleased me to see that. So if disk 7 reports the error, however, then that's enough information to the RAID software system here to say, oh, disk 7's a little suspect. Let's go get the parity, recalculate it, and then you will have the correct data returned. That's true. All those extra reads and checks add a lot of overhead and a lot that the CPU has to deal with. And ZFS and Linux MD cannot touch the IOPS or throughput that you can get from this kind of a solution, because this kind of a solution is closer to the hardware and can rely on hardware automation, things like DMA and GPU Direct for speed. So the storage medium itself is responsible for the data integrity, not the RAID system. The RAID system only gets involved when a disk is missing entirely, or one of the constituent disks in the array gives a clue to the RAID software that it should not be trusted, like a read error. And so where's the misunderstanding? Like, a lot of people are like, yeah, I'm validated. That's exactly what I said. In my methodology, I can inject an inconsistency that is not reported as an error by the drive. So you sort of start to see why it's absurd to assume that the drives will always be self-consistent. In the case of like a power failure, there's no guarantee that all drives in the volume would lose power at precisely the same moment. I mean, yeah, sure, enterprise class drives themselves, they technically do have something called power loss protection, PLP. There's little capacitors. There's stuff in here that makes sure that the internal journal of this drive will be self-consistent when it loses power unexpectedly. They know they're going to lose power just a moment before they actually lose power, and their little capacitors will keep them going for a moment or two. And that's fine, but that's not transitive all the way up the stack to all drives in a group would be self-consistent with each other. When this one loses power, it might not be the same time that another one loses power, and the power loss capacitors don't actually guarantee that the data buffer is written out, it's just the internal journal in the drive is written out. Grade has added a double journal to deal with exactly this situation, which has an impact on the write speed. But they have clearly used, you know, peer-to-peer writes and processing on the GPU side to minimize this as much as possible. This is an advantage over LinuxMD. LinuxMD does have some different journaling options to try to deal with the RAID 5 write hole and get the drives back in sync as quickly as possible after an unexpected event. That's true, but the approach here is really interesting. Secondarily, Grade also added features to deal with transient PCIe errors, which is awesome. Things like those AER errors or noise on the PCIe bus. PCIe doesn't necessarily have automatic transaction retry. They're doing that now under the hood, which is nice to see. That is a kind of a new feature. The real fix for this is the T10 data protection standard. Kioxia actually has a really nice blog entry that explains T10, and I've referred to this before, and this is a really nice way to close the loop on all of this. Folks like me that are worried about it and have an eye toward, you know, that full stack data protection with relatively low overhead, you know, are the reason that this standard exists. It really does close the loop on the type of bit rot that I'm talking about that can creep in, so you should check out that blog post because that sort of explains what I'm talking about. Grade doesn't use the T10 you know, data sector currently, but for people like me that are worried about it and have an eye toward that full stack data protection with low overhead, but dealt with at a RAID volume level, that's why this exists. Now, this might seem like a lot of words and verbosity around these points, but I think it's critically important that you, dear viewer, have a clear mental understanding of how this works so that you can make, you know, an appropriate evaluation and that you understand how these systems work and what they're designed to protect you against. The more important bits that you want to store and maintain, the more paranoid your thinking should be. I mean, that's just useful, right? But today we want to go fast. Bottom line here. On the one hand, I'm impressed with the amount of engineering that has gone into this solution. I mean, there are certain customers and workloads where you need the speed, you need the throughput, and a reasonable amount of fault tolerance. On the other hand, I'm sort of widely known as being sort of pedantic about data integrity. When there is a black swan event, you know, bit rot could creep in here, but they have implemented a lot over the last couple of years to detect that sort of thing, and they've added scrubs and that sort of thing, so that's good. And the types of expected, unexpected failure modes that can happen with this type of solution, it does actually work as advertised, so it will catch and correct those types of issues. I also tend to, you know, do things like migrate assembly, like migrate the volume across hosts and try to reassemble them. And I was quite pleased that much of that administration documentation is there and that basically all of that worked, even when migrating from an Intel host to an EPYC host. So I'd say that's better than average. This solution cannot touch something like ZFS for data integrity, however, or even BTRFS, like BTRFS RAID 1. But ZFS is an order of magnitude slower, at least. ZFS cannot touch this solution for speed. And the speed of this solution and the speed that it maintains in RAID 5 or RAID 6 modes, even in failure modes, is pretty impressive. Now, from here, for the future, I think there is a possibility of something special with this kind of a solution. So if you're into administering pools of data that go beyond, you know, a single chassis, it's also worth understanding the engineering trade-offs with the different solutions. You can do a clustered solution like Ceph with this as the underlying storage system in a single node, but when you have a problem, you're gonna, you know, just sort of write off the entire node. With ZFS and then Ceph and something like that in a cluster, it can better detect file level bit rot in that kind of a configuration. But with this, you can detect file level bit rot with a Ceph cluster built on top of this. So maybe that's something I should explore next or fart around with and just see how that goes. I don't know yet, I haven't tried that. Understand also when I'm talking about CPU utilization, a lot of the time I'm not talking about direct I/O to the block device, like just the overhead, because as you can see in a graph here, it's like CPU utilization is like 1%. But the reality is that I've got BTRFS K-workers. That's not G-RAID, that's just the overhead of the file system, and that's fair. And that is a significant amount of CPU when you're moving at 16, 20, 80 gigabytes per second. That's going to eat into your CPU. FIO itself is also using a significant amount of CPU as we're doing this kind of test. And this particular volume is based on 8 drives, not 16, so it's not going to perform the same way because I'm testing latency and all this other sort of stuff. But we still have our GPOL workers that are in the background doing things with I/O. I mean, it is true that a lot of the CPU overhead here is going to be down to the file system and like the stuff that you're running other than just artificial jobs, but it is something to consider. And also my load average, like 34. Realistically, our CPU overhead now is like, it's 38%, 10% CPU utilization. This is just, the overall system CPU utilization. Nevertheless, the CPU, like direct memory access, and the CPU is doing work for the RAID system beyond just peer-to-peer and direct memory access and everything else. There are actually kind of a lot of landmines. Ubuntu 24.04 LTS out of the box, at least at the time that I'm doing this video, is kernel 6.8. That is a long-term support kernel, and that is fine, and that's all well and good. However, it also wants you to install the NVIDIA driver the old way, the proprietary way. I couldn't get the installer to recognize the installation when it was via the GPL installation for whatever reason. And it also wants the driver to be present in DKMS. So when you run the pre-installer, it checks to see if the driver is there a couple of different ways. You can also get into weird situations with Ubuntu where you're mixing, if you had it installed the MIT GPL way and then you go back to the proprietary way, sometimes there can be a version mismatch, 570 versus 575. And I'm a little surprised this installer has not been updated to work with the MIT GPL installation alternative that NVIDIA has been offering for most of 2025 at this point to get your drivers installed. There's also a little bit of a caveat to be careful, like, hey, even though you're on an LTS supported distro, and there's this idea of LTS supported kernels that are newer than 6.8, it's not necessarily a guarantee that it is going to have day 0 or even week 0 support for those drivers. And I think that's something they'll need to address if they get proliferation with this product. And there are occasionally little quirks in the error messages when you go off script, like, it may cause the SupremeRAID driver cannot work properly if you insist on operating it. I get the gist of what they mean, but there's little things like that in the messaging in the program as well as the documentation, but they're working on it. Understand also that in addition to the whole proprietary versus MIT GPL version of the NVIDIA driver, there is another interesting thing coming down the pike, and that is the GPU peer-to-peer, GPU direct stuff. That is actually changing. So in kernel kernels newer than 6.8, and also CUDA drivers, CUDA 13, the peer-to-peer stuff is deprecated. That's not actually a bad thing because there are kernel primitives that are more generic for a lot of PCIe devices for peer-to-peer, and NVIDIA is actually embracing open standards. They're going to have to implement the Linux kernel standard ways of doing peer-to-peer, which NVIDIA is also building on. And so in newer kernels and with newer CUDA, that's probably the direction that they're headed in. And for now, support at kernel 6.8, I bet they're hoping that bridges the gap. But that's something you should be aware of if you're considering this solution and you're looking at, hyperconvergence and you need some of the new features of newer kernels in order to do that. I was not expecting I was not at all expecting it to work as well as it does in 2025. It works quite well. They've put a lot of engineering into it. I'm Will, this is Level 1. I'm signing out. You can find me in the Level 1 forums. But yeah, seriously though, let's go deeper. Let's try to find some stuff that we can run on this and just see how it runs. All right, I'm signing out and I'll see you there.